this network analysis exam that useful data attachment was the title. I'm not getting the means. I'm not getting what's there in this mail. Can you explain about it, please?
Could you please repeat it? Useful data?
Ma'am, I got a mail. The subject was useful data attachment. I'm not getting it. What they are trying to say in that mail.
Uh, like I don't follow. They sent you a mail with useful data as a attachment?
Ma'am, yes, ma'am. Ma'am, this was the mail.
Okay, I'll just check it. So there will be whatever the mail you will probably receive a mail. There will be an attachment in it, like some file will be attached in it.
Ma'am, no file was attached in that mail.
No, no. When on 30th April, this will be online, right?
Yes, ma'am.
On 13th April, while giving the exam, when you will receive the mail, there you will have attachment where they will mention all the instruction, the required formulas that will be given to you, and all those things will be given as an attachment.
Okay, ma'am.
So it is written like you see in the later part of the mail, this useful data details will be configured as the first question in the system. So you have to refer to the this attachment which will be sent to you on 30th April, and there will be no hard copies in the sense they won't send you hard copy paper or whatever to you.
Uh, okay, ma'am.
So with whatever attachment you will receive that day, you will have to look through it and solve whatever is given in the examination.
Okay, ma'am.
Yeah. Do you have any other specific doubt? Then you can ask. Otherwise, we'll just solve one of the assignment that we have missed earlier.
No, ma'am. I just want to ask that only.
Okay, okay, I see. Okay, then I'll start off with a few of the problems in switching circuits. So, okay, hello everyone. Welcome to the 12th and the last
Hi,
interaction.
hi, madam.
Yes.
Madam, in chat,
You're
सर
not,
मैं एक मैडम बोलो तो
you're not,
मैडम वाला रहते हैं ना तो उसमें ज़्यादा कौन ज्वाइन करता है सर वाला लिखती नहीं
I'm not able to hear you properly. Uh, could you repeat it?
लाइट में सर
Could you please type it in the chat box because I'm not able to hear you out. There is a lot of like noise and I can't hear you. Sorry? Uh, Murshid, if you are able to hear me, if you are asking something, I'm not able to hear you properly. You either type it in the chat box or, you know, use some other audio device because I'm not able to hear you. Uh, Murshid, if you're trying to ask a question, please type it in the chat box because parts of your sentences are only audible. If you're not asking anything, then mute yourself, please. Okay, I guess I'll start off with our few problems that I have lined up for today. This is for the capacitor and inductor circuits where switching was done like at a certain point of time t. This assignment we had skipped earlier because we wanted to keep up with the course assignment that was coming up. So I have a few problems for that and one or two extra problems on that. So yeah, welcome to the 12th and the last interaction session of network analysis. I am Depanita. So uh, let us look uh, like let us look into few of the problems with respect to inductor and capacitor. So in the first problem that we have today is that the current through a initially uncharged capacitor is given as shown in this figure. You have to calculate the voltage in the capacitor at time t equal to 1 second, and in the question it is written as enter a positive number, whatever it is. So suppose one capacitor, it has been connected to a certain source. We do not know, like the diagram is not given here, only the current and the current waveform with respect to time is given here, and you are asked to calculate the voltage across it at a certain time t equal to 1 second. So for the different point to point to time intervals, the current waveform is given, and if and the capacitance here is given, which is 50 microfarad. So in order to calculate the voltage across this capacitor, if you are given the the time, the current waveform, how can you calculate what is the relation between voltage and current in case of a capacitor? Vc is equal to 1 by say integration it dt, right?
Yes.
Yes. So in this case, it is written initially uncharged. That means this ideally should be minus infinity to a certain time t. In this case, t here is 1 second. We have to find up to 1 second. So we have to find 1 by c integration minus infinity to 1 I of t dt. Now, if you see at t less than 0, the voltage across the capacitor is 0 because it is written it is initially uncharged, right? So we only have the portion from 0 to 1, integration I of t dt. Now, integration of a function, like if you have a function f of x, so if the function is somewhat like this is x and this is f of x. So integration of f of x into dx will be the area under this curve. So in this case also from 0 to 1, that is from this point to this point, whatever the area will be under this, you will have to calculate in order to get the value of this integration. And C value you already have, so you can calculate Vc. So C here is 50 millifarad. So it is 50 into 10 to the power minus 3 or 0.05. So this will be 1 by 0.05, and what is the area under the curve? So we can do it part by part. So let us divide it into small portions. So what will be the area under this curve? This is a kind of a rectangle, right? With one side it is 5 and the other side is 0.2. So the area under this curve will be 5 into 0.2, right? So it will be 0.5 into, sorry, 5 into 0.2, not 0.5. So it will be 5 into 0.2 plus this big rectangle. So here the length is 10, it is given as 10 ampere, and the breadth is again 2.2. 0.2 second, right? So it will be again 10 into 0.2. Then again this third triangle, the area will be again 0.2 into 5. So which is so 2 times of this. And again for the bigger like the next 0.2 second, it will be 10 into 0.2. So we can just multiply this by 2. For zero point 0.8 to 1 second, since the current waveform is showing a magnitude of 0, so there will be no voltage there. So the area under the curve will be this portion multiplied by 2. So it is 1 by 0.05 into 2 into, so this is 5 2s 10, 1 plus 2 3. So 6 by 0.05 or 600 by 5, which is around 120 volt. Is this clear?
Yes, ma'am.
Okay. So next we'll look into another problem. So since you guys have already covered this assignment, I would like you to do it with me. So a 200 microfarad capacitor is connected across a voltage source whose voltage is given when it is less than 0 second. It takes the form of 5 volt, and if it is greater than 0 second, it takes 5 into t to the power minus e to the power minus t volts, where t is in seconds. We have to calculate the energy in millijoules stored in the capacitor at t equal to 1 second. So what is the energy that gets stored in the capacitor? Energy is equal to
half CVS square.
half CV square, right? So here we have to find the energy stored at the capacitor at t equal to 1 second. So what will be the value of V, uh, from the condition of the voltage across a capacitor which is given, what will be the value of V? C is given as 200 microfarad, so it will be half into, this is C. What will be V? Right. Since it is 1 second, so we will choose when t is greater than equal to 0, right? So it will be 5 into e to the power minus t square. So if I just cancel this, it is 100, and so this is 0.1 into 25 e to the power minus 2t. Now we have to find the energy at t equal to 1 second. So energy at t equal to 1 second will be 2.5 e to the power minus 2 into 1. So it will be 2.5 by e square, or divided by, so it is around 338.3 into 10 to the power minus 3 joules, or 338 millijoules, since it is in the question it is asked to find in millijoule, right? So now next, suppose if in the question it is asked what is the energy dissipated, for example, instead of 1 second, in the question it is asked what is the energy dissipated between 0 to 1 second. What is the energy that is getting stored inside the capacitor between this time interval t equal to 0 to 1 second? That is, how will you find out? So in the question it is asked, in the previous one it was asked how much energy is stored in the capacitor in at time equal to t equal to 1 second. Now if it is asked what is the energy stored in the time interval 0 to 1 second. How will you find that out? So how can we find out? Delta E will be equal to E at t equal to 0 second minus energy at t equal to 1 second. Whatever will be the energy difference, that will be stored in the capacitor between this time interval, right? So at this part we already figured out, right? This was 338 millijoule, right? In the previous question we had already calculated. So for t equal to at time t equal to 0, so E at t equal to 0 will be half Cv square at t equal to 0. So it will be half, C is 200 microfarad. So let me just, so 200 means 0.2, 200 millifarad, sorry. So it is 0.2. In case of V at time t equal to 0, see, even at equal to 0, this function will be valid because this is only for t less than 0. But less than, greater than equal to 0 will be 5 into e to the power minus t. So it will be 5 into e to the power minus t square, or it will be 2.5 e to the power minus 2t at t equal to 0. E to the power 0 is 1, so it is 2.5 joule or 2500 millijoule. So what will be the energy stored during this time interval? It will be 2500 minus 338, which is 2162 millijoule. So from time interval 0 to 1, in 1 second, the capacitor is storing this much amount of millijoule energy in it, right? I hope this is clear. Then we can move to the next question. So for the next question, you have to calculate Vc at steady state. Okay? So a circuit is given where there is a resistor, two resistors are connected, and across this 10 ohm resistor, a capacitor of 10 microfarad is connected. In the question, it is asked to calculate Vc at steady state. So you must remember the current and voltage waveform of any capacitor, right? So for example, whenever there is a load connected, whenever there is a voltage source connected across a capacitor, how will the voltage waveform change? So if a voltage of let's say value E is connected, so the voltage waveform is somewhat like this. So it will go and saturate up to a certain point, which will be around equal to the value of E. That is, here it is at t when it tends to infinity. So basically at infinity, capacitor acts as a open circuit. That is, the entire voltage appears across the capacitor. So since in the question it is given it is at a steady state, so this will be open circuited. If this is open circuited, that means no current is flowing in it. So basically the circuit reduced to the two resistors, right? This Vc is actually the voltage that is appearing across the capacitor, which will be equal to the voltage that is appearing across this 10 ohm resistance. So if we figure out what is the voltage across this 10 ohm resistance, we can calculate Vc. So the voltage across 10 ohm resistance, if we just use voltage divider rule, it will be 10 by 10 plus 40 into 2, right? So it will be 10 by 50 into 2, or 0.4 volt. So at steady state condition, when the capacitor is acting as an open circuit, the voltage that the capacitor plates will develop is around 0.4 volt. Is this clear? I hope like you're following. If not, then please do ask, or we can move to the next question. So in the same circuit itself, when it is at a steady state, you're asked to calculate the power in milliwatt being dissipated at the 40 ohm resistance, right? So during steady state means the capacitor is acting as an open circuit and there is a voltage of 0.4 volt that is getting appeared, which is equal to the voltage across this 10 ohm resistance. So there will be some current that will be flowing in the circuit. Here it is 2 volt. So we have to calculate the power that is getting dissipated across this 40 ohm resistance. For that, we either need to calculate the current that is flowing through the 40 ohm resistance or the voltage that is getting appeared across this 40 ohm resistance, right? Since we have already calculated the voltage, or we may as well calculate the current. So whatever the current that will be flowing in the circuit can be given by, if you apply KVL, it will be 2 volt minus I into 40 minus I into 10 will be equal to 0 if we apply KVL. So this will be, I will be equal to 2 by 50. This will be the value of current. So the power that is getting dissipated across the 40 ohm resistance is I square into R. Here I is equal to 2 by 50 whole square into R is 40, which is equal to 4 by 2500 into 40. So this comes out to be 16 by 250, which, let me just calculate, 0.064 watts, or we can write it as 64 milliwatt. I hope this is clear. Then these are like in this capacitor and inductor, like then when we will perform switching, all these are pretty simple. You just have to calculate it carefully. So in the sixth question again, it is given that there is an inductor of 100 millihenry where the voltage across the inductor is given by Vt and the current across the inductor is given by It, and the current waveform is mentioned with respect to time here. So we have to calculate the inductor voltage at a certain time t equal to minus 500 second, right? So for inductor, what is the relation between current and voltage? So voltage across an inductor is given by L into di by dt, right? Right? So L is given here 100 millihenry. So L equal to 100 into 10 to the power minus 3 Henry or 0.1 Henry. Now the current waveform is given in the question. So for inductor voltage at t equal to minus 500 millisecond. So that means it is around minus 0.5 second, right? So where will it lie in the region? It will lie somewhere around here, right? So basically the current waveform at that time is denoted by this line from which rises from 0 to 2, from minus 1 second to 0 second, because this is the time interval which is between minus 1 and 0 second. This is this particular slanting line that is going up. So in like in order to calculate the voltage, you need to have the slope of this line. Di by dt means the slope of this particular line. So it is basically, so how do you calculate the slope of this line? So let's say m is the slope of this line. It will be the change in current by the change in time. So the change in current is 2 ampere. It is going from 0 to 2 ampere. So it is 2 minus 0 by, and the change in this thing time is minus 1 to 0. So it is 0 minus of minus 1 second. So it is 2 by 1 or 2. So di by dt is actually 2. So at t equal to 500 millisecond, minus 500 millisecond, L is L di by dt. So L into di at minus 500 millisecond by dt, and we have already calculated this part is equal to 2. So it is 0.1 into 2 or 0.2 volt. So the inductor voltage at 500 millisecond is 0.2 volt. Similarly, if you are asked at a different time interval, let's say at t equal to 1 second, you will have to calculate the inductor voltage. So again, the inductor voltage at t equal to, let's say 1 second, will be L di at 1 second by dt. Now if you see in the interval from 0 to 1, current is constant. So ddt of any constant value is 0, right? So L will remain as it is, which is 0.1 into di by dt will become 0. That is, the voltage across the inductor at t equal to 1 second will be equal to 0 volt. Now if it is asked for the next section, that is if t equal to 0.25 second, 0.25 actually lies between this 2 and 3. Again we see that the current waveform has a slope. So in this section it was a constant value, so di by dt became 0 and hence the voltage became 0. In this case again there is a slope but a negative slope. So of course di by dt will be present and we can calculate VL of t at 2.5 second, right? Again VL of 2.5 second will be L into di by dt at 2.5 second. So in this case if you see, so if I calculate the slope of this line, it will be del I by del t. In this case del I changes from 2 ampere to 1 ampere, so 2 minus 1, and the time changes from 2 to 3, so it changes by 1 second, so it will be 1 by minus 1, so it is minus 1, right? L is equal to 0.1 since it is 100 millihenry, and di by dt at 2.5 second will have a negative slope, that is minus 1. So the voltage will be minus 0.1 volts. So you see, this will be very straightforward problems. Only thing is, remember to take the negative slope, and in this case it is the positive slope. So all these things you should do carefully, otherwise you will make a mistake with the sign and end up getting it wrong. Okay. So let's move to another question. So in this case, find the current IL in milliampere at steady state. So in case of an inductor, if you remember, whenever it is connected to an external voltage, at steady state, the current waveform saturates, right? Whatever the the current will be, if there is an external voltage E and if it is connected, suppose with a resistance, so the inductor voltage rises and finally saturates. That is, it acts as a short circuit, because if you remember the voltage waveform in case of an inductor, suppose if this is the voltage waveform, it initially rises and then falls down and assumes 0 at t increases, right? So if you remember, V of L t is given by whatever the voltage that is appearing across it minus e to the power t by tau, where tau is the time constant, which is R by L in case of an RL circuit. So, sorry?
IL is equal to 12 milliampere.
What is the 12 milliampere, did you say?
Yes, ma'am.
Yes, it is correct. So, yeah. So at steady state, inductor will act as a short circuit. So you will only have these two resist. So the circuit will be somewhat like this. Since this is a short circuit, no current here, no current will flow. So whatever the current will flow like this, which is 24 volt and 2 kilo ohm. So what will be the current that will be flowing will be equal to 24 by 24 by 2k. 2k is the resistance value. So it will be 12 into 10 to the power minus 3 ampere or 12 milliampere. Now what will be the VL at the steady state? What will be the voltage across the inductor? The voltage across the inductor will be equal to 0 because it is acting as a short circuit, right? Even if you look through the formula, VL of t, which is given by let's say some certain constant V naught e to the power minus t by tau, right? So when steady state means time goes to infinity, which will be V naught e to the power minus infinity by tau, which is 1 by e to the power minus infinity by tau is infinity only, right? So this will be infinite. If we take it up, it will become 0. So irrespective of whatever the resistance or the inductance is connected at steady state, the voltage across the inductor will always be 0. That is, it is a inductor is a acting as a short circuit, right? So can you please try this particular question? This is a certain circuit that is connected where you will have to figure out the value of Vx and Vxy, assuming that the circuit is running for a long time. This running for a very long time means it is at a steady state. That is, t is tending to infinity. So under this condition, what will be the value of Vx and Vxy? Can you please try this out? So since it is at a steady state, how will the circuit reduce to? So this voltage source will remain as it is, plus minus 5 volt. At steady state, the inductor will act as a short circuit. The resistor will remain as it is. So this is 20 ohm, this is 10 ohm. Now the capacitor will act as an open circuit. The inductor will act as a short circuit. The current source will be, in the reverse direction. So the current source will be in this direction as it is. This is the 15 ohm resistance, this is another 15 ohm resistance, and the inductor will be short circuit and the capacitor will be open circuited. So the circuit will reduce to this. Now we actually see like there are four resistances basically and two sources. So we can easily apply superposition theorem in order to calculate what is the voltage across this 15 ohm resistance, right? So initially let us keep like this 5 voltage source, and when one source is taken at a time, in case of superposition, what will happen? The current source will get short circuited, because in case of superposition one source is taken at a time and rest of the sources are replaced by their internal resistances, right? So this 5 volt will remain as it is. So I'll just draw the circuit in a more simplified manner. So this is 20 ohm. The current source is now, so sorry, current source will be open circuited, right? Because it is replaced by their internal resistances. This is the 15 ohm resistor and 15 ohm. This is Vx, and this part is X and Y or Vxy. So now it is just one simple circuit. We can just apply KVL across this loop and calculate Vx, right? So since this is like taking one source at a time, we will put this as Vx1, because again we will
Yeah,
have to, sorry,
the value of Vx is equals to minus 28.5.
yes, you are right. Sorry. So in this case, Vx dash, we can either apply KVL or you can use voltage divider rule in order to calculate it. So let's say Vx dash is 5 by, sorry, it is 15. So it is 15 by 20 plus 15 plus 15 into 5, or it is 15 by 30 plus 50 into 5. So it is Vx dash is 1.5 volt. So Vxy will be the voltage across the two 15 ohm resistances, right? So it will be 15 plus 15 by 20 plus 15 plus 15 into 5, or 30 by 50 into 5, which is equal to 3 volt. Now if I just take the second source, so let me just copy this. So now I am taking only the current source now. So the voltage source will be short circuited. So this will be X and Y or Vxy. Now only this the current source is 5 ampere. So this 5 ampere current source exists, and these two are 15 ohm resistances. This is 20 ohm. Now whatever the current is flowing from this node, it will get divided into these two resistances. So one side there is 30 ohm resistance and the other side there is 20 ohm resistance. So we have to calculate this I1 and I2. We can use current divider rule here. So I1 will be, current gets divided in the reverse ratio of the resistances, right? So it will be 20 by 50 into 5, or it will be 2 ampere. So Vx will be equal to the resistance into the current, 15 into 2. Let this be Vx double dash and this be Vxy double dash. So it will be 30 volt. And I2 will be, since 5 ampere current is there, so it will be the reverse ratio. So it will be 30 by 50 into 5, or 3 ampere. So Vxy will be equal to the voltage that is appearing across this 20 ohm resistance. So 3 into 20. This will be Vxy, or 60 volt. So using superposition, if we just look into this circuit, so Vx dash and Vx double dash is, the polarity of the voltage is like this. In case of this circuit, since current is flowing in this direction, that means whatever 30 volt we are giving as Vx, it is actually minus 30 volt, because current 30 volt we are getting in this direction, but Vx double dash we have assumed to be in the reverse direction, so it is minus 30 volt. And in this case also, if you see, current is flowing in this direction, so ideally it should, this side should be positive, and the this since current is coming in this way, so this is positive, this is negative, right? So in case of xy, this ideally should be negative, but this is positive, but we are taking vxy in the reverse direction. We are taking this to be positive and this to be negative, so it is minus 60 volt. So the actual Vx will be Vx dash plus Vx double dash, which is, so it is 1.5 volt minus 30 volt, which is equal to minus 28.5 volt. Similarly, Vxy is equal to Vxy dash plus Vxy double dash, which is equal to 3 volt minus 60 volt, or minus 57 volt. I hope this is clear. If yes, then let's move to the next question. So in this case, it is written that the capacitor was initially charged to 10 volt. That is, before the closing of the switch, the capacitor had an initial voltage of 10 volt. Then at t equal to 0, the switch was closed, and we have to calculate the time required for the capacitor to discharge to 1 volt. Since there are no external sources here, whatever the current will flow because of the voltage that is initially stored in the capacitor, and we have to calculate the time that is required for the capacitor to reach 1 volt. Can you please calculate this? So it is given in the question, Vc0 minus is equal to 10 volt. The voltage across a capacitor cannot instantaneously change, so this will be Vc0 plus. So when the switch is closed, the circuit is somewhat like this. And this is 10 millifarad. So let this be Vc. Since these two are connected in parallel to each other, right? Yes? Sorry?
T is equal to second. 230 seconds.
230?
Time is just
Sorry?
second.
Yeah. Yeah, it will be around 230 seconds. So if I just apply KVL here, suppose a current I of t is flowing across it. So the relation between VC and I of t is, in case of capacitor, let's see, like suppose if there is a capacitor like this and current I of t is flowing, then the voltage VC is given as, so, or the current I of t is given as C dV dt, right? But in this case, if you see, VC, the positive, from the positive terminal the current is flowing. In this case, from the positive toward to the positive terminal the current was entering. So in this case it will be minus C dV by dt, minus like in case of this, I of t will be minus C dVc by dt, right? So in this case I of t will be minus C dVc by dt, and this same Vc is actually the voltage across this 10 ohm resistance, right? So this will be equal to the current that is flowing in the resistor, or V by R, or Vc by R. So if we just write it, minus C dVc, this is as a function of time dt, is equal to Vc by R, or dVc by Vc will be equal to minus 1 by Rc integration of dt, sorry, 1 by Rc dt. Now if I integrate, integration of 1 by Vc into dVc will be equal to minus 1 by Rc integration of dt. This is ln Vc is equal to minus T by Rc plus some constant. This constant I can assume it to be a logarithm of some number, so I can write it as ln Vc equal to minus T by Rc plus ln of something, let's say A. So if I bring this in this term, so ln Vc Vc by A will be equal to minus T by Rc. So if I remove the log, Vc by A will be equal to e to the power minus T by Rc. Here Rc is R and C, the value we know, and we also know, let's just calculate the time constant T equal to Rc, which is equal to 10 millifarad into 10 kilo ohm, which is 100. And it is given at Vc, so this will be V of t. So Vc of t will be A into e to the power minus T by 100. Now it is given that the initial condition is 10 volt. So Vc at 10 volt will be equal to 10, which is equal to A into e to the power 0 at time t equal to 0. So basically A is equal to 10, right? So we can write the voltage equation as Vc of t is equal to 10 into e to the power minus T by 100. Now it is asked in the question, what is the time required in second for the capacitor to discharge to 1 volt. That is, Vc will have to be equal to 1 volt. So this 1 will be equal to 10 into e to the power minus T by 100, or e to the power T by 100 will be equal to 10, right? If I take log both sides, so it will be T by 100 equal to ln 10. Now log of 10 is 2.33025. So the time will be equal to 100 into this, which is 230.25 second, which you have calculated the time required to reach 1 volt will be around 230.25 seconds. Okay, I hope this is fine. Then we can move to the next question. The switch is closed at t equal to 0. Before that, no current was flowing through the inductor. How much time is required in second for the inductor current to reach a value of 0.8? Can you also calculate this? So in this case, like I of 0 minus is equal to 0. That is, no current was flowing across the inductor. So as soon as the switch was closed, the current started flowing, but current across an inductor cannot instantaneously change. So following the law, we have to calculate how much time is required for the current to reach around 0.8 ampere. So at t greater than 0, when the switch is closed, the condition of the circuit is like this, right? So 1 ampere, this is 2 ohm, this is 1 Henry. So this 1 ampere gets divided into these two branches. Let this be IL and IR. So at this particular node, if I apply KCL at A, I'll get 1 will be equal to IR plus IL, right? So whatever the voltage will be across this inductors, the same voltage will appear across this resistor, right? In case of an inductor, VL is given by L di by dt, right? So in this case, since L is equal to 1 di by dt, right? So if I just replace this like IR will be equal to VR or VL, which is equal by 2 plus IL. So I'll write IL now as I of t. Now VL can be replaced by this L di by dt, right? L into di by dt. So it is half into L is 1 dIL.
Ma'am,
Yes.
t is equal to 0.8 second.
Sorry. 0.8.
8 second.
So the answer is around. Let me see. Just one.
Okay, ma'am.
So it is around 0.8 second.
0.8 second.
Yes, yes, 0.8 second.
Yes, ma'am.
Yeah. So please note that this is just a function of time, and for now I am writing this to be IL. Okay. So now we have an equation like this. So I'll just simplify. dIL by dt plus 2IL will be equal to 2. I'm just showing like how even like if you don't remember the formulas, you can still solve the circuit and get to the equation, right? So in this case, if you see, this 2 contributes to the integrating factor. So as sir has shown in his lecture, this will be actually d dt of, so if I just multiply e to the power, so this is the integrating factor, e to the power 2 into t. So I'll multiply this on the both side, e to the power 2t dIL by dt plus 2 e to the power 2t into IL is equal to 2 e to the power 2t. Now this part of the integration is actually, if I differentiate d dt of I into e to the power 2t. If I differentiate it by parts, then I'll end up with this expression. This will be equal to 2 e to the power 2t. di of e to the power 2t equal to 2 e to the power 2t into dt. Now if I just integrate, it will be I e to the power 2t will be equal to 2 e to the power 2t by 2, right, plus some constant c. So if I get rid of, if I divide e to the power 2t both sides, this will be I into 2 will get cancelled. So this will be 1 plus c into e to the power minus 2t. Now this is the inductor current equation. Now what we have to do is apply the initial condition in order to calculate the c, right? So it is 1 plus I of t is equal to 1 plus c e to the power minus 2t. Now at t equal to 0, we know inductor current is equal to 0. So 0 will be equal to 1 plus c into e to the power 0. So c will be equal to minus 1. So the inductor current that we have now is 1 minus 1 e to the power minus 2t. Now you are asked to when the current will reach 0.8 ampere. So this will be equal to 0.8 will be equal to 1 minus e to the power minus 2t, or e to the power minus 2t will be equal to 0.2. So if I just take log on both sides, ln minus 2 will be equal to ln of 0.2, right, which comes out around minus 1.609, something like that. So t, this minus minus will get cancelled, t will be equal to 0.804 second. This is what you got, right? Yeah. So from the previous question itself, can you please calculate how much is the total energy in joule that is delivered or supplied by the current source? What will be the total energy? So energy is given by integration of p into dt, right? So it is minus infinity to infinity, but like as up to the time 0, there is no current, like since the inductor current is not flowing. So whatever the energy is getting delivered by this 1 ampere source is actually what that is getting dissipated in the 2 ohm resistor or getting stored in the 1 ohm source, right? So before switching, only the resistor was connected, and like this t equal to like this switch was open, so nothing was getting stored in the inductor. But in this case, it is asked how much total energy is delivered or supplied by the current source after the switch is closed. That is, from time t equal to 0 to infinity, you will have to figure out the energy. For that, you have to calculate this power. Power is equal to V into I, right? So we have the current, which is 1 ampere. Now we have to find the voltage across this current source, which is equal to actually what the voltage will be across this inductor, right? And we have already, I guess, calculated the current across the inductor, which is I equal to 1 plus e to the power minus 2t. So we have I of t is equal to 1 minus e to the power minus 2t. So VL also we can calculate. VL equal to this, whatever the voltage across this inductor will be the voltage that is appearing across this 1 ohm resistance, right? So VL will be equal to L di by dt. L is 1 Henry. Now d dt, we have the current waveform, that is 1 minus e to the power minus 2t. So d dt of constant is 0 minus d dt of e to the power minus 2t is e to the power minus 2t by minus 2. Right? Sorry, it will be not divided into minus 2. It is differentiation, right? So it will be 2 into e to the power minus 2t. This is the voltage that is appearing across the inductor. Now the voltage appearing across the 1 ampere current source will be the voltage appearing across the inductor because they are all connected in parallel. So P will be equal to 2 e to the power minus 2t into I. Here I is 1 ampere, which is 2 e to the power minus 2t. Therefore, the energy that is getting dissipated or delivered or supplied will be, in this case, since the current, there is no other source and the current source is applying, like it is delivering current, feeding current to the inductor, which was initially uncharged or there was no current flowing through it. So this is basically delivering or supplying the power. So this will be equal to 0 to infinity P is equal to 2 e to the power minus 2t into dt. So it is 2 integration 0 to infinity e to the power minus 2t dt. This is equal to 2 into minus 2t by minus 2 from 0 to infinity. I'll just take the minus 2 outside, so it will be minus 2 by 2. So e to the power infinity, e to the power minus infinity minus e to the power 0. So this is minus 1. E to the power minus infinity is equal to 0 and e to the power 0 is equal to 1. So this will be equal to 1. So 1 watt of energy is getting supplied from this 1 ampere current source. Is this clear? If yes, then we'll move to the next question. So in this question, there are two switches, S1 and S2, and in the question it is given that this switch S2 has been closed for a very long time. That means very long time means when the S2 was closed, this part of the circuit which contains this inductance, this resistance and this voltage source, this is at a steady state because S2 is closed for a very long time. Then at time t equal to 0, S1 is closed and we have to find the rate of, this is rate of change of current through the inductor at just t equal to 0 plus. So can you calculate this? I'll just give you 2 minutes to calculate. If not, then we will solve together. Could you please try this out?
Yes, ma'am.
Yeah. Are you able to do it? So S2 is closed for a long time means the second part of the circuit, like which has this inductor, this resistance, and this voltage, this has achieved steady state, right? This part of the circuit has achieved steady state, which means at steady state the inductor acts as a short circuit, right? So it is basically the inductor is acting as a short circuit, and whatever the current is flowing is in this particular loop. So this I is equal to 3 by 2 or 1.5 ampere, right? This is the condition before S1 is closed, right? Now at t equal to 0, when S1 is closed, now the circuit is like this. So this is 3 volt, this is 1 ohm, this is this 2 ohm resistor, this is 3 volt. So the current initially was flowing like this in inductor, right? And it had 1.5 ampere. So in case of inductor, current cannot change instantaneously. So just after switching, whatever the current that was flowing at I0 minus will be equal to the current that is flowing at I0 plus. This we have found out to be 1.5 ampere, right? Because this was the initial steady state condition when only one switch, which is S2, was closed. So this 1.5 ampere through the inductor will keep on flowing, and as soon as the switch is closed, it cannot change instantaneously. It will change gradually. So right now this 1.5 ampere current is still flowing through the inductor, because you have to find like the condition that is asked, that is the rate of change of current through the inductor at t equal to 0 plus. 0 plus means just after the instant of switching, and rate of change of current means actually di by dt. You have to figure out what is di by dt. Now under this condition, can you calculate what is the rate of the current that is flowing, like what will be the rate of the current through the inductor just after switching? So just assume VL is the voltage across this inductor. So basically this node voltage is VL, because it is connected, this is connected to the ground, right? Now at this point A, can we apply KCL? Because you see this 1.5 ampere current will keep on flowing at just time instant t equal to 0 plus, which is infinitesimally small when the switch is closed, like very small amount of time has elapsed. So if I apply KCL at A at just time t equal to 0 plus, what will happen is whatever the current that will be flowing here and flowing here and flowing here will be equal to 0. So the let this be I1, this be I2, and this is 1.5 ampere, right? So I1 plus I2 plus 1.5 ampere will be equal to 0. Now I1, this voltage VL will be, this since this is the node voltage, so it is VL minus 3 by 1 plus VL minus 3 by 2 plus 1.5 will be equal to 0. This this VL is actually a function of time, right? VL. Now VL can be written in case of an inductor, if this is the VL and the current is flowing in I of L. So VL can be written as L di by dt. L is 1 Henry. So VL is just di by dt. So I'll just simplify this. So this will be 2VL minus 6 plus VL minus 3 equal to 3 plus 3 equal to 0. So 3VL is equal to 6 or VL equal to 2. Now VL is again equal to di by dt. So we have VL equal to di by dt, and this again VL is equal to 2. So di by dt is equal to 2, which is what we want in the question. What is the rate of the current through the inductor? So the answer is the rate of the inductor through the current is 2 ampere per second, since I is in ampere and T is in second. Is this clear? I hope this is clear to you. If yes, can you try the next problem? So this is kind of similar, you see, but like the switching conditions are different. So this S1 switch is closed, is S1 is open for a very long time, and it is closed at t equal to 0. So until t equal to 0, this circuit is already at steady state. Now what is I of t at t greater than 0, that is after the switch is closed? Can you please try this one? So maybe calculate, I'll just give a specific value of t. So calculate I of 0.55 second. What will be the value of this? Can you please calculate this one? Okay. Maybe then I'll just move ahead with it. So uh, S1 is open for a very long time, which means this circuit initially is already at a steady state, where this is the current, this is a resistance, current source of 10 ampere, this is a resistance of 5 ohm. Since it is still not closed, so this is the 5 ohm resistance, and at steady state inductor will act as a short circuit, right? So inductor is shorted. So now whatever the current, this 10 ampere current will get distributed evenly because both the resistance are same. So it will have 5 ampere and 5 ampere flowing through it, right? Now you will have to calculate what is I of t at t greater than 0, that is after the switch is closed. So when the switch is closed, this is the 10 ampere current source, this is the 5 ohm resistance. Now the switch is closed, so this is a short circuit, and this is the 5 ohm resistance, and this is the 2.5 Henry inductor. Now current through an inductor cannot instantaneously change, so this 5 ampere current is still flowing through the inductor. So let this be VL. Now you will have to figure out what is I of t, what is the current that is flowing in this particular branch. Since this is short circuited, this 5 ohm resistance, let me take the highlighter, this 5 ohm resistance will become redundant because there is a short circuit across it. So I can reduce the circuit like this. It is this 10 ampere current source. There is a short circuit here, and there is this resistance and inductance, in which just from the before the switching condition 5 ampere current was flowing. So current through an inductor cannot instantaneously change. So now we will see like what happens. Like let us assume that the voltage across the inductor is VL, and we will see like how the current is changing. Now if you just look at this part of the circuit, like up to this part of the circuit, so now what will happen, this inductor will, whatever the energy it is storing, it will start discharging it. Now already the current was flowing in this direction, 5 ampere current was flowing in this direction, so the current will continue to flow in this particular direction, right? So the inductor will start discharging through this new like when S2 S1 is closed, through this short circuit, right? So whatever the current will be flowing here, I of t will be a summation of current that is getting discharged from the capacitor and the current that is flowing from the current source, right? So for only let us consider only for the resistive and inductive circuit which are connected in series like this. So let us just calculate what is the current that is coming out of the inductor after the switch is closed. So you know, in case of an inductor, the current cannot change instantaneously, so I of L of t will be whatever the initial current that was flowing into e to the power minus t by tau, right? Here tau is equal to L by R. L here is 2.5, R is 5 ohm, so this is tau is equal to 0.5, right? So IL of t, I naught here initially a 5 ampere current was flowing, so it is 5 into e to the power minus t by 0.5 or 5 into e to the power minus 2t, right? This is the inductor current. So basically if I just consider this branch, a current that is getting contributed by the inductor is actually 5 e to the power minus 2t. Now if I consider the entire part of the circuit, so let me see if I can just, no. So I'll just grab this portion of the circuit. So from the inductor, what current we are getting is 5 into e to the power minus 2t. And from here, from the current source, 10 ampere current is flowing here. So if I apply KVL like at this particular node, so current is actually flowing, like if it is moving in this direction, which means this 5 e to the power minus 2t current is flowing out of this node. So now I will just apply KVL at this node A. KVL at A. So if I apply KVL at A, it is equal to 10 is equal to I of t. 10 is the current that is flowing into the node, and I of t current is flowing out of the node, which is this, plus 5 e to the power minus 2t. This is the KVL equation. So we can easily figure out now I of t, which is equal to 10 minus 5 e to the power 2t, right? Now in the question it is asked, suppose at a certain time like 0.55 second, what will be the value of the current flowing through that branch, that is the short circuit branch. So now just plug in the value of t. So I of 0.55 second is equal to 10 minus 5 e to the power, so sorry, there is a minus here, 2 into 0.55, which is equal to 10 minus 5 into e to the power minus 1.1. So this comes out to be 10 minus 5 . So this is around 3004. This comes out to be 1.664. So it is around 8.336 ampere. So in this question, if you see, like the condition of current through the inductor, which cannot change instantaneously, needs to be valid. So even though this circuit was at a steady state, and now because of this switching condition, this is connected, this branch is connected, for example this A to B branch is connected, as the current through the inductor cannot change instantaneously, it will continue to supply this I of L for the new condition, and the total current in this particular branch will be summation of what this source is providing and what this inductor is discharging. Then after a certain time, like the inductor may or may not get completely discharged, and it will anyway it will get discharged in the waveform like this. So I hope this is clear for you. Then we'll move to the next question, or the last question for today. So in this case again, like there is a voltage source which is connected with a resistance, and a switch is open for now, like it is open for a long time. That means this circuit at open condition is at steady state, and there is 1 Henry resistance inductance connected with a 4 ohm resistance. So we'll have to figure out what is I of t, just the the equation of I of t at t equal to 0 plus, that is just after switching. So we have to find the condition first before switching, and then consider, take into fact that the current across an inductor cannot change instantaneously, and then finally calculate I of t at t equal to 0 plus, right? So just like at t less than 0, or t is equal to just before switching, t equal to 0 minus, let us look into the condition of the circuit. So since it was at a steady state, so the inductor is short circuited. Sorry, the voltage source will be there. So this voltage source of 12 volt is here. This is the resistance. This is open and the inductor is short circuited. So this is 2 ohm and 4 ohm and 12 volt. So whatever the current that will be flowing in here will be equal to 12 by 2 plus 4, 12 by 6 or 2 ampere. So this 2 ampere current is actually flowing through the inductor under steady state condition. Now after the switching is done, so now the circuit is, this 12 volt is appearing across it, the resistance, there is a short circuit here, and this inductor. So the inductor, through this inductor the current cannot instantaneously change. However, what can we say here? So whatever, for example, this IL is flowing, it will try to flow. So in this particular loop the current will flow like this. So IL is actually coming out of this node. If I consider this node to be A, now since this is like shorted, that means the voltage here is equal to 0, right? So let this be I1 and we have to figure out I of t, right? So if I apply KCL at A, it will be equal to I1 will be equal to I of t plus let's say IL, and we had already calculated this IL, which is equal to 2 ampere. So 2 and I of t here right now we do not know. How can we calculate I1? So if you see, if we consider only this part of the circuit, so this is short circuited. So here it is 0 volt, right? Here the node voltage is 0 and this is 12 volt and this is a 2 ohm resistance, right? So whatever the current that is flowing through this 2 ohm resistance will be equal to 12 minus 0 by 2, which is 6 ampere, right? So I1 is equal to 6 ampere. So I of t is equal to 6 minus 2 or 4 ampere. I hope this is clear to you. So since we had like missed this switching conditions and of RLC circuits earlier, so I had discussed a couple of problems of the same. In case you have any doubts, you can post it in the forum and the TAs will look into it. And this is all we have for today. So this brings us to the end of the session and good luck for your exam. Thank you. I'll just stop the recording now.